In any inert gas, you have a bunch of neutral particles. You're bound to have a couple charged particles just floating about. Just from thermal fluctuations. So if you apply a large voltage and electric field, that charged particle is going to go down the field and eventually bump into the uncharged particles. If the electric field drives it fast enough, it'll strike these other particles with enough energy to pop off an electron, separating it into a positive ion and an electron. Now suddenly we have 3 charged particles, an electron, 2 ions. They're going to travel down the field lines and start breaking apart more and more particles in something of an avalanche effect. This is how we generate plasma. Now, electrons and atoms have different energy levels. And what that means is, depending on the energy level, there's a different amount of energy it takes to pop that electron off of the atom. It's ionization energy. The closer to the nucleus, the stronger it's being held on, the more energy it takes to pop it off. The further away from the nucleus, the easier it is to knock an electron off. Conversely, if you already have an ion with some electrons popped off, electrons will lose energy by rejoining with the atom. That same amount of ionization energy. What happens to that energy is it gets re-emitted as a photon. The wavelength and frequency of that photon depend on the energy that was used to emit it, which depends on which energy level the electron dropped to, or if the electron was transitioning between 2 different energy levels. The simplest example of this is with hydrogen, since hydrogen only has 1 electron to begin with. The amount of energy it takes for an electron to transition down to the n equals 1 energy level, the Lyman series, usually corresponds to ultraviolet light, which we can't see. But electrons going to n equals 2, the Balmer series, are well within the visible range. And in a chaotic plasma, like mentioned earlier, we will be seeing electrons transitioning between all energy levels. And we'll be able to look at each individual wavelength using a simple spectrometer, which diffracts light into its constituent frequencies. This is a gas tube filled with hydrogen gas. This device is going to apply an electric field that's going to create a plasma using the avalanche effect we mentioned earlier. Here we see the light from hydrogen being diffracted into discrete wavelengths, corresponding to specific energy transitions. Now, this can be done with other gases, such as helium, mercury, and of course neon.